Right, good afternoon. Thank you very much for joining us today. This is a presentation from the Smart Mobility Living Lab in London. Running order for today, if my screen moves forwards, hopefully it does. James Long, who is the solution architect for the Smart Mobility Living Lab, will be our host this afternoon and introduce the presenters. So we'll kick off immediately now. James, would you like to introduce the event and context behind it?
Hi, good afternoon, everybody. Hope you can hear me. Thank you very much for joining. So on behalf of Smart Mobility Living Lab London, I'm really happy to welcome you to this session. We've got a great talk coming up on the virtual validation of automated vehicles. So my name's James Long. As Penny says, I'm the solutions architect for the Smart Mobility Living Lab. The Smart Mobility Living Lab is a testbed facility located across 2 areas of London. We've got the Queen Elizabeth Olympic Park up at Stratford and the Royal Borough of Greenwich. This has been designed and built to enable both the development, testing and trialling of new mobility technologies and services in real-world urban environments. This has been established using a combination of government funding via Innovate UK and industry funding by a consortium including our delivery partners at Cisco, Cubic, DG Cities, the London Legacy Development Corporation, Loughborough University, TRL and Transport for London. It's also part of the wider Testbed UK initiative. The Smart Mobility Living Lab has been developed on both physical and virtual test and development facilities. And I'll explain a bit about the reason and rationale behind that in a second. So the physical part of Smart Mobility Living Lab consists of 24 kilometres or 15 miles in old money of instrumented public roads in London. This is then supported and underpinned by a comprehensive set of communications infrastructure, which feeds into data centres, control rooms, and the like. This ultimately enables our clients to develop and operate new technologies, gather independent evidence on their performance, and fundamentally understand their impact on their environment and other road users. So as well as investing in the physical facility, we've also invested significantly in the tooling, digital twins and validation metrics to enable customers to develop and test in the virtual world. This combination enables us to create truly representative digital twins that have a direct correlation and link to the real world. This means that the Smart Mobility Living Lab is able to fundamentally support its customers in developing and trialling the virtual world before seamlessly moving across to our real world facility to validate and verify those simulated marks. We consider this feedback loop to be as critical as anything, as it enables the virtual world to be populated with those edge and corner cases that have been observed in the real world, and ultimately helps us to close that gap between the virtual and real world testing. This aligns very closely with the content of today's session as we understand how the Smart Mobility Living Lab environment has been utilised in other projects to start to look at that virtual validation. So I'd now like to introduce Chekia Gimbash, who's our BIM guru, and David Hind, who is one of TRL's chief scientists who has a long-standing involvement in vehicle regulation. Those guys will present some of our recent work that's been undertaken in this field, and afterwards we'll have a Q&A. What I'm going to ask everybody to do is to try and present their questions by sending me a private message using the chat function at the bottom of the screen. I should be appearing at the top of that list as 0-James Long. We'll try and answer as many questions as the time permits at the end. I'm now going to hand over to David first, I believe, who should have control of the screen.
Okay, so thank you, James. We're going to take a look at some work that we performed mostly under the Streetwise project. So I'll give a little bit of an introduction to Streetwise. And really for TRL's point of view, Streetwise built on work that we did within the Gateway project and other projects like Driven and Move UK and other Innovate UK projects that we've been involved with. And of course, the development of the Smart Mobility Living Lab in London. So the funding for the Streetwise project came from the Industrial Strategy Challenge Fund and was delivered via Innovate UK, with other investment coming directly from industry. So in total, it was a £15 million grant. Apparently my chat is coming up. Apologies for that. £15 million grant with £10 million going to 5AI, now 5, and £5 million distributed amongst the other partners, which you can see there. The project started in September 2017 and went through to February 2020. So the Streetwise project aimed to develop and demonstrate the technology, safety validation methods, insurance and service models required to deliver an automated shared mobility solution targeted at replacing the personal urban commuter car. So it sought to answer quite a range of questions. There's a few examples on the screen at the moment. So looking at how a shared mobility solution might be integrated with public transport, what the licensing regime for that sort of thing might be, and how members of the public might perceive the safety of automated vehicles, how might the vehicle be insured, and what the certification implications might be for an automated vehicle. So all of this was tackled through a number of work packages. So in the first work package, which was primarily 5AI with the University of Oxford, was primarily involved with the development of the vehicle platform itself and all of the core technology around the automated driving system. So a very large amount of effort within the several years of the project within that program of work there. The project also looked at the safety and insurance implications for automated vehicles. And so TRL's main involvement in this section of the project was to look at development of the safety case to support safe trials of the 5 vehicles on public roads near Millbrook and then ultimately in London. We also had a service aspect looking at licensing and route selection to integrate appropriately with public transport and those kind of things. And it also involved a trial of the vehicles towards the end of the project. So over 100 people had the opportunity to experience a 20-kilometre ride, out and back ride, representing a shared commuter trip between transport hubs on a route that was not well served by public transport. So we undertook interviews and surveys that were conducted before and after the experience. And this provided insight on attitudes to AVs and, in fact, very pleased to report, generally very positive attitudes to the automated vehicle experience. And finally, we had a program to look at regulation and implications for regulators and insurers, certification and risk. So this is basically what we're going to talk about today, or at least TRL's component of this work package. So we looked at what might be needed for an independent certification of automated vehicles. What information might a regulator or insurer want in order to supplement the evidence provided by a vehicle manufacturer or an automated driving system developer? So we're continuing to look at some of these issues in other projects, including further work on safety cases, and also on this kind of simulation and validation and certification work. But the presentation today will focus primarily on the work that we have done in Streetwise. So Checky, are you ready to roll?
I am indeed. Can you hear me?
Fantastic. Yes.
Okay, thank you very much. I shall then try to share my screen and hopefully all will be fine. Can anyone? I guess you can, because I can see from my second laptop. All right, thank you, David, and thanks everyone for joining us again. Let's first have a look at the generic question we're trying to answer. What is the main thing we're trying to answer? So let's start with today's vehicles. We're looking at a Nissan EMV 200 vehicle you can buy off the shelf, an electric van today. And for vehicles such as these, as most of you are already aware there are a number of regulations about crash testing, front and side impact regulations. There are also a voluntary crash test, such as Euro NCAP testing program. There are regulations in place about the emissions to ensure the health and well-being of the public. We also have systems in place, such as the MOT system, to ensure once this product is on the road for a certain amount of time, it is still in a roadworthy condition and it is in a safe, it can perform in a safe way. And when we come to the driver, we have a number of requirements, as you all know. We have the driving and theory test to ensure on paper the driver and on practice the driver know what to do. We have hazard perception test, which is a form of edge case preparation for the human driver. And we also have the mechanism of enforcement and penalties to try and remove those which are not behaving in a safe manner. Now, what we're trying to do with the technology of automated vehicles, we are basically trying to replace Mr. John Smith there with something else. What are we trying to replace him with? With the systems on board of this vehicle, as we have in our Smart Mobility Living Lab vehicles. You can see, obviously, there are cameras on board. There can be LiDAR. There's LiDAR on board. And we often have radar systems on board, which are effectively coming together and replacing the sensory inputs of a human being. And then these inputs, instead of the human brain, are then fed into the hardware and the software on board of the vehicle, which are making the necessary decisions to drive this vehicle, and hopefully safely. So we have replaced Mr. John Smith with all these systems on board and hardware and software. Yet, how are we going to replace all these regulations in place to ensure this person is fit to drive and also continue to monitor the driving behavior once it's on the road? We envisage this, and most of the industry envisages this, to be done through lots and lots of different types of testing and different levels of testing. First off, here you're seeing a digital twin of the SMLL, the Smart Mobile Living Lab in Woolwich. And in fact, here, if you can see my cursor, that's where our new offices and garages are being built at the moment. So we basically need to test these vehicles in many different levels. First off, obviously, in a closed environment, we need to make sure the systems on board are performing in a certain way. And then in test labs such as SMLL, we need to ensure they can perform properly in real-world conditions. But to supplement that, we also need the virtual testing, the virtual validation part of it, simply because the sheer scale of the driving required to fully validate these vehicles. You may have heard numerous different sources quoting billions and billions of miles. I personally read an article where a major manufacturer was quoted of saying a fully autonomous vehicle, automated vehicle, needs to be driven around 8 billion miles for it to be fully validated. Obviously, all these high numbers are related to the chance of living through the edge cases. And by edge cases, what we mean are those incidents which are rare and very challenging for the vehicle, that only occur when very rare human environment and vehicle factors come together. And this is where the virtual validation shines, because even if we manage to replicate the incidents for a specific version of a vehicle, there will be software updates. Are we going to do another 8 billion miles of travel for each version of this? It's just not practical. So there needs to be the physical testing needs to be supplemented with the virtual element. And this world is a dynamic world. There are different times of day, different weather conditions, different actors, which we can control in the virtual counterpart. For example, when this gentleman is jumping in front of the vehicle, we would ideally like this to happen for the first time in a virtual world, and we are happy with the behavior of the vehicle. The other questions are, what happens when the sun is shining right into the cameras, for example? Challenging situations brings to mind one of the famous incidents that was on the media. If you remember, an automated vehicle driving in automated mode is driving side by side with a white curtain side truck. The sun is really low, sun is about to set, which ends up affecting the contrast on the cameras. So the white curtain side is very high contrast, almost looks like empty space, and the automated vehicle is driving right into the truck. An edge case which can only happen when a certain type of vehicle combined with certain environmental factors, certain time of the day, and certain position. So we want to be able to tap into all these combinations in the virtual world. For example, when it's raining really heavily, with the system or when it's snowstorm, edge cases where all the lines on the ground are covered, or maybe even the signs are covered with the vehicle, able to perform satisfactory with the other. So basically what we try to answer in Streetwise project is, first off, we need to prepare this vehicle for certain scenarios. And what are those scenarios? What scenarios should we prepare this vehicle for? And then the next thing is, once we decided the relevant scenarios, how are we going to bring these into a simulation environment and carry out these simulations in a mass scale? And once we carry out all these simulations in a mass scale, we will end up with lots of results. And we need to understand how are we going to interpret these results. So in the next 3 parts of our presentation, we will go into the details of these and try to explore these concepts a bit further. Over to you, David.
So, thank you. Very noisy weather.
Oh, was it? Sorry.
Indeed. So that looks a little bit at why we might want independent certification, looking at how that some aspects might replace the current governance of how a vehicle and a driver is allowed on the road. Of course, a vehicle might be approved at the international level, but we think it's important to have a local element, a national element to certification, to check all sorts of things, like it works with the local infrastructure, such as signage, that the vehicle understands and correctly handles local driving norms, and not least for the UK, because we drive on the wrong side of the road compared with most of the countries where vehicles are being developed at the moment. So all of this will help ensure public confidence in automated vehicle technologies. So next up, we will look at what is required to develop scenarios to test the AV. Checky, back to you.
Okay, thank you again, David. Let's go back into it. Hopefully weather will be quiet this time. Here we're looking at an incident, a single incident with 2 serious injuries, and immediately what I see in this picture is an opportunity to prevent these injuries with the help of automated vehicle technologies, because we are in a very ambitious target here. We are trying to implement this technology to help reduce the casualties at the end of the day. And there are many, many types of incidents happening every day on the Great Britain roads. And in fact, if we look at the total numbers, we're on average for the last 5 years looking at around 685 collisions per day, of which 75 are serious injury, and there are 5 fatalities. When I look into this picture, I see a massive opportunity to intervene and perhaps replace the human error with much capable systems, and perhaps maybe we can reduce the numbers. So what we wanted is we wanted to tap into this as our starting point, because ultimately this is the first thing we want to eliminate with this technology. So what we did is we start with the Great Britain level data, which most of you may know is kept in Stats 19, where all the injuries incidents are recorded. And when we look at the Stats 19 data, we have over 1 million incidents in the last 5 years. Now, this is a lot of data and a lot of incidents. And how were we going to bring in these things within a manageable level in our Streetwise project? Basically, we developed something we call the a priori dashboard, which is basically a system to filter the bulk data to group these incidents into most common and perhaps most relevant types for the simulation in this case. So we can bring them into the simulation. For example, maybe there were the majority of the incidents were T-junction incidents in single carriageways, or perhaps a more common, a less common one was a rear-end shunt and roundabouts. But the difficulty with this data is, yes, there is a lot of it, but how much information is there for us to do a meaningful simulation? And let's try to demonstrate that difficulty to you through this specific incident, where it was a fatal incident on a dual carriageway, 40 miles per hour speed limit, with a single vehicle involved, and it was near a junction. Let's get into the details of this incident and try to replicate with Stats 19 data alone. Okay, so what we know there was a single vehicle, but we do not know, and we know the direction, yes, but we do not know if that vehicle was in the first lane, second lane, or third lane. In fact, we don't know in which part of the lane or where exactly the impact point was. We know there was a single pedestrian involved. We do not know, again, the position or direction, which means this impact could have happened in anywhere. And this is not really giving us anything meaningful to the level that we can use in this simulation. And this is thankfully where the RAIDS comes in. Now, for those of you who does not know, RAIDS, who do not know, RAIDS is the acronym for Road Accident In-Depth Studies. This is a program run by DFT for over 10 years under different names. Basically, what happens in RAIDS is at TRL, we have a collision investigation vehicle with collision investigators on call. And when there is an incident within a certain radius of our location, we attend to the incident and collect much more detailed information about each and individual incident. So what we decided to do, we basically decided to match those common cases with those that are found in the rates cases, so we can understand a bit better of what were the actual causes for this incident, what is the interesting and important aspect of the incident we want to replicate in the simulation. So let's compare these things. Again, back to stats 19, we almost have a 2D view, everything is in flux, it could be anywhere. And when we go into rates, almost we are seeing a 3D view of the world. We know much more about infrastructure, for example. We know where the lines were, if they were visible or not. We know the location of the specific infrastructure which may have an effect on the result of the incident. We know much more about the individual phases of the incident, such as distance, position in the carriageway, distance from the edge of the road, for example. We know much more about the road geometry, surface friction, temperature, that kind of information. We know again about different phases of the incident. We know point of perception, reaction, point of impact. But you see, there is something that doesn't add up here. If this vehicle saw that person jumping in front of it from such a distance, why on earth did this incident happen? By the way, this is a real incident we're trying to show, but so far it's been based on the stats 19 understanding of this incident, because the stats 19 did not record the most single important part of this incident. There was a bus there blocking the view, which was waiting to turn left. And this again was based on a real incident. It did not occur in this specific location, but very, very similar location. And as a result of this, the incident happens. So basically, wrapping it all up, what we've done is we started with stats 19 Great Britain level data. Using the prior dashboard, we filtered into the relevant cases to be used on Streetwise, and we selected relevant scenarios as a minimum for this. And then we found matching scenarios from rates to enhance the data to understand, to parameterize each individual incident. And then we fed those into the simulation. Back to you, David.
Okay, thank you, Jackie. So just to summarize, that shows how one might build scenarios that are nationally representative, yet have the level of detail that is required to truly test the automated driving system. And of course, there's only one source of scenarios. One might look at very many other sources for scenarios, but I think it's a very important source to have scenarios that relate back to situations in which it's known to have gone wrong for human drivers. So we can ensure that the automated vehicle is at least better than the human drivers in those situations. So next we will look at how one could implement the simulation process itself. Is that a good way to describe it, Jackie?
Yes, that is. But just, I want to add one thing I forgot to mention, just to add on what you were saying. Yes, in this project we mainly focused on the real world incidents for human drivers, but obviously with this workflow, what we envisage many different data sources that can be plugged in the future through various formats. For example, could be the open scenario format, and we envisage sources such as maybe insurance records for property damage only incidents which are not recorded at the moment in stats 19, or maybe even in the future we envisage similar to rates, maybe a specific data set, database to collect information specific to automated vehicles. But back to your question about simulation. Okay, we decided which scenarios to carry forward to the simulation, and now we need a simulation environment, which brings us to back to our environment. Now this is showing a LiDAR scan, a 3D point cloud of again the area I was showing earlier in Woolwich. This digital twin started in a previous Innovate UK project. Actually, it started in a project called BIMCAV, which was about showing the potential benefits of building information modeling to support automated and connected vehicle technologies. And under this project, we started developing a number of areas and BIM models for different areas. And as the Smart Mobility Living Lab continued to evolve, we invested more on these and got more of these models built into different levels of fidelity. Now, obviously, we start with the point cloud on which the BIM models were built. And for some selected areas, we also invested further to actually apply textures and explore a much more visually appealing version as well. But this model alone is not enough for us to bring this into the simulation platform. For simulation, we decided in this project to use the Carla open source simulation platform, which is a widely used simulation platform for automated vehicle research. And it's open, so it's very easy to develop and get support from the wider community. But to bring, again, this geometry, we need to support it with the OpenDrive file, which is basically a file format to describe the geometry that is matching what we have already, which needs to be fed into the simulation. So this is showing the OpenDrive representation of the specific area and what the simulation is needing to get to that level. And once we are there, we then introduce specific traffic rules, for example, where vehicles need to give way to each other in traffic calming measures such as these, waiting for each other, so that the other vehicles, not the ego vehicle, but the other vehicles in our simulation can behave in a representative way to a certain degree. Once we get to that level, the next stage was to focus on our ego vehicle, and now I'm going to show you a recording from the simulation from Carla in the same environment. You can see on the left hand side, in this version we carried out on the BIM looking version, and then here you can see through the AutoWare and ROS bridges, basically we connected to the RVs on the right hand side for the visualization of the sensor data. So basically at this stage we had the necessary connection between the sensor data coming from the simulation, and we could access it and we could visualize it in the other software. And you can see here the additional information such as the distance to the relevant objects are also visualized. And once we got to that level, now we have the environment, we have the basic functionality of the third parties, and we have the necessary input and output system to access the sensor data and also provide input back to the vehicle so we can drive it. The next stage is to bring in the scenarios. This is where we created a version of the scenario runner, our own version with the Python client. Basically what it does, it generates the incidents that we thought would be relevant by placing the relevant actors in the relevant positions in the scene. And because they're parameterized, we can change this incident and create different versions of it. But obviously what we really want to do, we don't want to just recreate the same incident. We want to replace this vehicle with our ego vehicle that we are testing now, and everything else is the same as the incident. And now we see how the ego vehicle reacts. So what we've done is through parameterization, we carried out, I think, over 1,060 iterations of the same incident by changing, for example, the weather conditions, the time at which the pedestrian jumps, and the direction from which the pedestrian jumps. And these were run automatically in a sequence. And for all of these different iterations, we recorded the results, which then we fed into the assessment step. So to summarize what we have done, once again, we started with the selected scenarios, then through the description language, we fed them. We decided on which parts of the environment these needs to be done, and we created the environment by combining geometry and necessary OpenDrive data and other requirements. And then we had a simulation platform on which we controlled the actor, maneuver, time, weather, and all the other elements by the Python client. And into this simulation, we tap in by providing sensor output to the AV model, which then provides driving input back into the model. Through this loop, the vehicle is being driven in the simulation environment into the incident scenario. And at the end, we have a recording of the simulation. Back to you, David.
Fantastic, thank you, Czeki. So we have the physical testbed, and we have a very high fidelity reconstruction of the testbed in software, and we've seen that we can use that to run thousands of parameterized iterations of test scenarios. Again, either from real-world collision data, as demonstrated earlier, or based on measurements made within the SML itself or from other sources. So finally, let's take a look at what we do with all of those simulations. It generates a huge amount of data. What might some of the considerations be for evaluating the performance of the automated vehicle, and some of the issues that make it challenging? Czeki.
Okay, so let's tap into that. In this last part, we will be starting with 3 videos. In this video, you are seeing the ego vehicle is the orange one, and the blue one needs to brake harshly due to that cyclist. And what we see is the ego vehicle is using all the space that it has to go into the back of the blue vehicle to brake in the last moment as possible and lightly as possible within the given space. Now the question is this, yes, this is the no crash situation, but is this really what we want to see? What if during that braking, the vehicle encounters a surface which has less friction coefficient than the previous area, so it could easily lend itself to an error. And also perhaps people on board of this vehicle may not be the most comfortable in such an incident. So let's look at another version of this, or the other extreme. This time again, the blue vehicle brakes harshly for the cyclist, but this time the ego vehicle brakes as harshly as possible the moment it sees the danger, perhaps way too harshly, while it had all this space in front of it. Then the question is, what about the risk of a rear end shunt, which is increased in this situation? And also, again, this is perhaps not the most comfortable of situations for people on board. Perhaps what we want to see is this third demonstration, where the ego vehicle is using all the space, optimum level, and having a balance between harsh braking and how close it gets to the vehicle on front. So the reason why we show these 3 cases is assessing the performance of a vehicle such as this is not as simple as saying crash, no crash, yes, this is successful, no, it's not successful. It's much more complicated than that. In fact, it's perhaps a 3-way system where it's a balance between how fast the vehicle is going in terms of how useful the vehicle is for day-to-day transportation, and how safe it is going, because if the vehicle is going very, very slowly, perhaps maybe it's the safest, but it's not performing its function. Or perhaps if it's using all the space and doing all this harsh braking, perhaps it's not the most comfortable. So there needs to be a balance in these cases. But the main point is crash, no crash is not just enough to come to a conclusion in these scenarios. Now, going back to our vehicle in here, what we have done in the Streetwise project, basically we have developed our simple assessment methodology for this project. We started by defining certain zones in front of the vehicle. For example, the red one here represents the unavoidable collision zone, which means anyone inside this zone will cause an incident because the vehicle does not have the necessary space to slow down in that kind of speed. The orange area represents avoidable but harsh braking zone, and the green one is representing the safe zone, which goes forever actually for that. Now, in this case, you're seeing a very simplified rectangular shape, but in reality, this is not a rectangular shape. It's much more complex, and perhaps it should involve multiple trajectories of the road users crossing each other and checking for all sorts of different cross sections all the time. Then what we introduced in this project was we developed something we call the reward function. Basically, we assign a score to the vehicle based on its speed, acceleration, and crash no crash criteria every time step of the assessment. And for each of the undesired performances, the vehicle is accumulating penalty points, and we can have a fail threshold. So we can say if this vehicle accumulates more than this many points, then this is not acceptable for this specific scenario. So let's look at the time step 1 in this case. Here we see the vehicle, let's say the vehicle is having a proper speed within the speed limit, and there is no harsh deceleration and there is no crash, so it hasn't accumulated any points. Similar for time step 2, by the way. Obviously this is just a simplification of the system, so one time step can look like multiple seconds in this, but it's not like that in the actual simulation. Again, everything is fine. But in the third step, in the simple scenario, the pedestrian jumps into the avoidable yet harsh braking zone, and the vehicle needs to brake harshly, which then ends up with it accumulating a simple acceleration score, but it doesn't go over the threshold. Now, this is a simple one. If you go back to the difficult case we had with the bus, try to go through the same scenario, what happens is this time the pedestrian jumps right into the unavoidable zone, and as a result, the vehicle slams the brakes, gets a negative score for deceleration, harsh deceleration, and obviously there was no way it could have avoided the impact, and as a result, it gets a penalty point for crash nose crash, and then we are over the fail threshold. But the question is, if the vehicle had no other choice, like if it was physically impossible to stop here, is it really a fail? I mean, what is the meaning of a fail if it's not impossible? You know, if it's not possible to do it, then perhaps maybe we should look at changing the criteria, and maybe we should compare it with what would the human driver would have done here if the human driver could have reacted faster than this, or maybe perhaps the vehicle would have reacted faster. Yes, there is a collision, but at least it did everything possible within the physics of the situation. But maybe I was wrong all along with what I was telling you. Maybe this vehicle failed long before it reached this point. What should have happened is, this is an urban environment. There are lots of parked cars in environments such as this. So perhaps this vehicle should have realized the bus on the left there, and actually it should have slowed down way before reaching the bus. And what would have happened then? All these unavoidable and harsh braking zones would have got much smaller, and at the time the pedestrian jumped in front of it, then the incident could have been avoided. So perhaps maybe we should not just evaluate these with human terms. We should look at what is possible, you know, what can be better in the future, more of a perceptive assessment methodology, which will be again very relevant in urban environments such as this, with lots of parked cars and all other unique challenges with direct access to the roads. So I guess this gives you a overall understanding of our approach here. Just to summarize what we've done, we started with the simulation scenario from which the simulation data is recorded in the end, which is then fed into the reward function. And for each simulation, we are calculating a cumulative score. And then however many iterations is decided for that specific case, we are running this loop many times with different iterations of the same incident. And in the end, we are feeding that information into the final evaluation criteria. Obviously, there is a lot that needs to be done here, which needs to be explored further. But just to sum it up, I'm going to very quickly go through the overall review of what we've talked about so far. So we started with the Great Britain level data from Stats 19, fed them into a priori dashboard to choose the most relevant scenarios to feed into this pipeline, and we enhanced the information coming from Stats 19 for the selected scenarios with data coming from rates. Then using the description language, we are describing which part of the environment these incidents will occur, and we're controlling all the actor maneuver through the Python code, and we are creating these parameterized scenarios. And during each of these scenarios, we have the necessary input-output system in place, and then we are recording the data coming from each simulation, and then we are feeding them into reward function, and we are coming with some sort of cumulative score, and we are running this many iterations and creating collecting all this data, and in the end we are coming with an evaluation for the overall performance of the vehicle. I think that kind of sums it up. I hope you found it useful. David, back to you.
So thank you, Czeki. Yeah, so there are lots of different considerations when evaluating the performance of the automated vehicle, and looking at the scenario that was just presented there. For instance, the automated vehicle developer could probably pass all of the tests by driving everywhere at 3 kilometers an hour, but then the vehicle's not going to be performing the function that we want of it as a society, whether that's transporting people around or whether that's transporting goods around. So I think it's important to consider the behaviors that would be encouraged in response to any certification scheme, any unintended consequences of those behaviors, and try and achieve an appropriate balance of risks, which I think is a really big challenge. So we've looked there at a very basic reward function, but we've used this as a stepping stone into helping us understand the complexity of the question that's being asked here about how we evaluate the performance of the automated vehicle and achieve a reasonable balance of the utility that we want from vehicles and the risks that they present to everybody else in the environment. So this has looked at a demonstrator toolchain that we are continuing to use in subsequent projects. And it's not that this is necessarily the ultimate toolchain that could be used at a sort of national level, but hopefully it allows ourselves and other UK projects to explore all of the aspects of independent certification that are relevant to evaluating the performance of automated vehicles. I think that's the end of the presentation, all the talk and talk. So back to James, I think, to coordinate questions. Thank you very much, everybody, for listening.
Hi, thanks very much then, gents. So we're now moving into the Q&A part of the session, where we've also been joined by Adam Barrow, who's TRL's Head of Collision Research. So thank you very much for the questions so far, they're really good. Please do keep them coming in. Just a reminder again, if you want to send a question, then select me on the list of the chat function at the bottom, which should be 0-James Long, and then I should be receiving those questions directly. So I'm going to direct the first question towards David, if that's okay, David. So
that's okay.
The environment itself. So how representative does that environment need to be?
Well, that might depend on what you're doing with it. So I think if you're, there's a reasonable amount of validation that's required before you can rely on the large amount of evidence that will have to come from simulation. And for that validation exercise, I think you'll need a very high fidelity representation of the environment, such as we have with the SMLL digital twin there. But it might be that for some aspects of evaluating the behavior of the automated vehicles and performing very large numbers of iterations of that evaluation, that you can get away with a slightly lower level of I don't know if you can hear in the background, but my Google has just been interrupting me. I do apologize for that. So, yes, so for large numbers of iterations of scenarios that are testing the behavior of the automated vehicle, it might be that one could get away with a lower level of fidelity in the model and be able to run more simulations in a shorter time period.
Thanks, David. And Jackie, I wonder whether you could add to that a little bit, just to explain about how within the Smart Mobility Living Lab environment, we've ensured we've got a valid representation of the real world.
Sorry, James, was that for me?
Yes. Do you want me to repeat the question?
Yes, please.
So how within the Smart Mobility Living Lab environment have we ensured that we've got a valid representation of the real world?
Okay, thank you. Right, so I guess I mentioned a little bit in my presentation. We have our work with the environment we use here has not started with Streetwise project. We started around 4 or 5 years ago with another project called BIMCAV, which is an Innovate UK project, and we started experimenting with BIM models and see how we can benefit from BIM building information models and feed them into the simulation platform. And actually, if I can share my screen for a moment here, I don't know if you can see it, but here, let me show you very quickly what we have done. So we started with this small area as a proof of concept, but as the project developed, Smart Multi and developed, we basically started getting all these side roads and everything built. We experimented with different levels of fidelity, and we tried using different file formats and bringing them into the simulation. For us, it started with a representation of the road and roadside infrastructure. Primarily, every single element of the infrastructure on the road, the surface of the road, was very, very important. The fidelity of that was very important, and to ensure every single thing on the road surface was captured. And then, as the project continued, we started using that environment and bringing them into different types of projects for different uses. So in here we are using a version of that for virtual validation, but there are also other versions which we use for example, human factors research in terms of virtual reality experiments and all that. I don't know if that answers your question. I feel like I'm going on a bit detail here, James.
I think that's fine for now. I'm sure we'll come back with more questions if there's a follow-up needed.
Thank you.
So James, we've lost you.
Am I back again now?
You are back. Fantastic.
I'm sorry about that. Sorry about that. So we've had a variety of questions along a similar theme, and this is linking really to the validation approach. And I'm going to direct this one towards Adam. So Adam, I wonder if you can comment on how we can develop a methodology to provide a consistent assessment of what acceptable performance looks like.
Hi, James. Can you hear me?
Perfectly, thank you.
Yeah. So I think what we've shown in the kind of the simulation and the presentation was a fairly simple kind of working example of what we've been doing with the reward function. We get the kind of the basic aspects of collision risk, and already behind that that reward function, there's a lot of equations and a lot of coding that goes into that. But it's worth thinking about the kind of the purpose of the reward function, and it's linked to ultimately safety. So the underlying kind of core principle is looking at the most important aspect of this, which is collision risk. So in thinking about this, we started off looking at what layers of risk feed into the collision risk and how we can codify that into the simulation. And it started really with the kind of at the base level. It's quite easy to draw a kind of a hard boundary around what is acceptable performance by thinking about things like kind of unconditional rules that can't be broken or shouldn't be broken at any point. So these are things like speed limit or running through a red light. Those kinds of things are never acceptable. Even when you've got an ambulance sat behind you, you should never go through a red light. So it's quite an easy aspect to kind of build into the reward function to say if at any point these conditions are broken, then we can feed that into score negatively or have a negative impact on the reward function. But it also gets a little bit more complex than that. So thinking about, if you consider a 30-mile-an-hour residential road, for example, it would be perfectly acceptable to travel through that environment, that scenario at 30 miles an hour. But if we add in a static risk element, things like parked cars along both sides of that road, narrowing the kind of available carriageway, all of a sudden that aspect means that traveling through that environment at 30 miles an hour is no longer acceptable. We wouldn't do that as kind of human drivers, and we wouldn't expect the AV to do a similar thing. So there's a kind of modification of the risk and understanding how we can code that into the simulation environment and kind of provide risk modifiers or modifiers to the reward function around these static areas of effect is a key development of that. And then kind of sitting on top of these static risk modifiers, you then of course have all the dynamic elements, which Cheki's presentation showed quite well, obviously in that case a pedestrian walking out. But understanding that all of the dynamic elements, all the dynamic actors in this scenario have their own kind of red, amber, green risk zones out in front of them. So it's not just looking at how the ego vehicle, the autonomous vehicle interacts with the actual vehicles, but also understanding how it interacts with the other risk zones and feeding that into the scoring. So yeah, I think that kind of gives an overview of some of the immediate developments, but it's also worth noting that this assessment approach is looking at the kind of the outputs of what the AV is doing and not looking at the black box, the decision process that's going on within the AV. We're just looking at what that AV has decided to do within this scenario. So we like to think that through various iterations of this process and developments of this process, eventually you will have access to the black box data, what's actually going on and the failure modes that are happening inside the autonomous vehicle. But there's steps that can be taken in between that. So we're also looking at Bayesian inference techniques to look at the overall, the outputs of thousands or even millions of these collisions to try and understand or infer how the CAV, the AV is perceiving risk and those thresholds at where that breaks.
Yeah, if I could just add to that. So the example you gave of the vehicles parked along the side of the road and wanting to modify the speed because the hazards are not quite so apparent. And the red light. So the red light is quite well defined in the rules of the road and the highway code and so forth, but some of the other things are not very precisely defined. So that's a little bit hard to encode in the evaluation of an automated vehicle. And it's the decisions that the developers of automated vehicles are having to make all of the time as to how they interpret those rules and implement them within their decision stack.
Thanks very much, David. So the next question is again back to the transferability of that validation approach and our evaluation methodology there. So I'm going to direct this one towards Checky, and ultimately, why have we selected this particular tool chain, and can it be used with other processes?
Thank you, James. Good question. Why did we select this specific one? I think it goes back to what we really wanted to achieve in this project. You know, we really wanted to have a positive can-do attitude rather than like getting bogged down in the specific details. We really wanted to showcase the whole process from start to finish with the tools available. So we didn't really develop any of these with the thought of, yes, it has to be specifically for the simulation platform, or yes, the data needs to come from this specific database. It was all about taking what's out there and get it done. And you know, even this presentation that we've done there is to get the message out there and you know, get the message across, because ultimately, you know, what we want to do as a country, even we want to push this area forward as quickly as possible. From that perspective, the data sources, for example, as I said in my presentation, it doesn't need to be just these data sources. It could be any different types of data sources. In fact, it needs to be more than this. This is a minimum requirement, in my opinion, that an automated vehicle should perform at least better than a human driver. But then the question is, with all these additional systems on board and all these you know, new type of decision making, we will introduce most probably new type of issues that are inherent to these vehicles. So there needs to be some data source so we can test for those specific situations. And then about the simulation environment, as I said, the model that we imported into this simulation environment was not at first specifically made for this simulation environment. It was made as a building information model to help us you know, run and build the facility. But we use that, and as the data is there, we can convert that into so many different formats and bring it into other types of simulation platforms out there. It is possible if there is benefit for it. And then finally, for the assessment part of it, as we, I think, strongly implied, we only barely scratched the surface on this. There needs to be much more work done about this in the UK if you want to take this forward. And yeah, there is no need why we cannot apply different criteria to the results collected, recorded from an incident. So in theory, you can change the code, the criteria, and come up with a different scoring completely with the same results. I guess that kind of answers the question you asked.
Thanks, Checky. In the interest of time, I'm going to ask one final question. Apologies if we haven't got around to answering yours. There's been an absolute flood of questions, so thank you very much for those. The last one's going to go to Adam, and this is really about future enhancements to the environment. Are there any additional data sets or data sources that we see as being valuable to enhance the data inputs to simulation scenarios?
Yeah, thanks, James. I think you could probably host a webinar probably just on this topic. So I won't try and cover all of the ground on this one. And I think Checky earlier did a good job of listing some of the kind of immediate data sources that could feed into this process and really add value to this. One of the key things I would say is the emphasis at the moment often is on collision data, because that's the best sort of incident data that we have. But a question we should definitely be asking is, should we just be limiting this to collision data and the edge cases that result in a kind of a road traffic collision feeding into this? What about the edge cases that didn't in real life turn into a collision, but could have if it was not an autonomous vehicle? But I suppose kind of focusing my answer down to the part that we know most about and thinking about the data sources that kind of exist and can support this process. We've used RAIDs quite heavily in this process as the kind of the best data source for understanding scenarios that happened in the real world. But there's certainly a lot that can be done to develop that whole in-depth kind of scenario generation for this purpose. So RAIDs is certainly not designed specifically to help or to generate scenarios and simulations of this kind of fidelity, though the information can be taken out and created as we've demonstrated. So I think, as Checky mentioned previously, thinking about a dedicated kind of CAV scenario generation data set that is grounded in the real world is really important. And also it's worth saying that when eventually we do have kind of CAVs out on the road and they do have incidents, a huge part of that has to be the kind of regulatory feedback mechanism of understanding and downloading what happened in that vehicle, access to the in-vehicle data, and feeding that into this process. A big part of RAIDS is understanding and investigating ADAS collisions, and we're understanding the challenges that exist today just in kind of level 2 SAE autonomy vehicles, just how difficult it is to access that information. So I'd say that kind of framework really needs to be in place to make the most of this.
That's great, Adam, and well done for finishing at 4:59. I'm afraid that's going to have to be the end of the Q&A. Lots of good questions being raised by lots of people, but I'd just like to say firstly, thank you very much to the speakers, to David, Checky and Adam for running through the presentations and handling the Q&A, to Penny as well for setting this up in the first place and running through the housekeeping at the beginning. And if you have any further questions around what we've been talking about today or the Smart Mobility Living Lab more widely, please drop us an email. It's on the screen at the moment. It's info@smartmobility.london. This is a really exciting area for us. We're already applying this more widely in projects, including taking more of a systems view and how that interacts on a simulation basis, looking at things like vehicle-to-vehicle, vehicle infrastructure comms. So there's a long way to go, but there's a really, really ripe scene of opportunity there as well. So thank you very much. Enjoy the rest of the day and the sunshine, should you have it where you are in the world. And we'll speak soon.
Yeah, and I'd just like to also say thank you to all of the partners from the Streetwise project. I think it was a fantastic collaboration, a really, really good spirit, and an awful lot achieved within that project. So thank you to everybody. I can see a few of the names on the call.